So what I'm going to do is really talk about the summary for policymakers that came out on the 27th of September. And I'll put a special preference around the human influences on the climate system because I was responsible for that particular chapter, and also because I think I'd like to dispel a couple of myths by the end of the talk about how important the human influence part is from the evidence, the scientific evidence. It wasn't me, of course. There were 259 authors involved in the Working Group 1 report. It was an enormous effort spread across 39 different countries. So this is actually the front cover of the Working Group 1 report. So for those who don't know, Working Group 1 and all of the IPCC reports are basically driven by the World Meteorological Organization and the United Nations Environment Programme. And so the first part of the group of 3 reports that are coming out over the next year is around the physical science. The second one will be around impacts, and the third will be around mitigation. The second one, which is actually discussed in the Telegraph as a leaked report, and that will come out in March next year. So the Intergovernmental Panel for Climate Change has been doing this for 20 odd years now. This current report was conceived in 2009 when we actually approved the outline. We, in 2010, authors were nominated, so you only get this on the basis a role in the IPCC process by selection. There was 259 authors selected at that time. The IPCC is unusual relative to the normal scientific community. The process of peer review, and I'll talk a little bit more about that in a moment, is very transparent. We responded to a little over 55,000 comments from 1,100 experts in this 4-year process. There are a total of 14 chapters, and there's an atlas actually, which is a resource for regional projections. But the bit that was important in late September was this thing called the Summary for Policymakers. The Summary for Policymakers condenses down roughly 1.2 million words into 14,000, okay? So the value of the report isn't this assessment of the literature, it's about this distillation down to 9 figures and 14,000 words. And actually, for those who struggle even with 14,000 words, there's 19 headlines that you can sum up in 2 pages. So there's a lot of work actually gone in to make this report kind of condensed, ready for people who make decisions and think about climate change at the periphery of their business. This is our chapter team. I have to say that IPCC is a wonderful experience to participate in because you forget about the guy in the middle. The rest are famous and are very clever. But not everyone likes IPCC. Jeffrey Sachs, who really is a Nobel Prize winner, says it's a remarkable example of mobilising expert analysis. Tim Flannery, I'm sorry about the colours here, but the key bit is he thinks the assessments are dull as dishwater. So not everyone loves IPCC. So this is our chapter, and just to kind of walk you through the process over the last 4 years, there's 15 lead authors in here. There's 3 review editors. And so why do we have review editors? It's because actually there's 3 stages of review. And each review in response to comments from governments and experts must be signed off by the review editors, right? So they, unlike peer-reviewed literature, we have to get sign-off from those review editors, and those review editors are there to make sure we actually take the comments from government seriously. And from the experts, right? So this isn't IPCC launching off in its own direction. It's about transparency, and it's about rigour, and it's about following the process. And just to give you a sense, in the first order draft we had 700 comments. By the third order draft we had 2,200 comments. Every comment actually is filled out in a spreadsheet and will be put up on the web, and you'll be able to trawl through it and actually match up how we responded to all of the government comments and all of the science experts over that time period. This is an extraordinary thing, and some people actually do PhDs on the analysis of the responses from the lead authors to the government documents. It's sort of an extraordinary process. So we do this for 4 years. And then we get to, there are 4 coordinating lead authors from Australia. So Australia actually has a really big footprint on this report. And it's something we should actually be proud of. And then what happens is we finally make the summary for policymakers, and we go to Stockholm. We went to Stockholm. And there's the pleasantries at the beginning. So these 2 guys here are the co-chairs of the full Working Group 1 report, responsible for the entire process. And what we do is there's 14,000 words, and so every line is literally gavelled down. So you start at the beginning and you read it out, and when 110 nations that are sitting out in front of you agree, you gavel the line down, right? And then you move to the next line, and the next. And 14,000 words is about 22 pages. We agree to the tables and the figures, and it can be high drama, because if you only get through 2/3 of the summary, the last third drops onto the floor and is never published, right? It might be the third that you care about because it's the projections of what the future climate might do. So you have to get to the end. You have to get to the end, and literally any nation could intervene and just disagree, okay? And you just may not get there. So it is kind of high drama. So on the end of the third day, we had 20% of words agreed. 75% of the time gone. The end of the third day, it turned out we started at 8 a.m. and we finished at 3 a.m. the next day. So on the fourth day, some of us struggle and fall asleep. But on the fourth day, we actually got to the end. And we put in a day that started at 8 a.m. and finished at 5 a.m. on the next day, okay? And then we went and had a press release just 5 hours later. So this gentleman here hasn't slept for, had 6 hours sleep in the last 2 days. But there he fronted up to the press conference. And I will now tell you what 110 nations have basically agreed on as part of these messages around the IPCC summary for policymakers. So this is the decadal average temperature record for the from the 1850s through to the last decade, 2000 to 2010. And the striking thing is that the last decade, in spite of a pause in the warming that's been talked about in the press, is actually the warmest decade we've ever had. Each of these decades are progressively warmer, and since the 1960s we've actually come 0.6 degrees, and since 1880 through to 2012 we've also come 0.85 degrees of warming. Okay, and if we look back into the paleo records, what we also find is that the last 30-year average, now 30 years is the sort of typical average that we take for defining a climate. The last 30 years is actually with a 66% probability likely to be warmer than anything in the last 1400 years for the Northern Hemisphere. Okay, so we've actually gone beyond the point of the medieval climate anomaly. In the report, by the way, we always use this kind of language, this likelihood. So we have a calibrated language to tell you about the strength and our confidence of the results. So something that says likely means that it's more than 2/3 probability. Very likely would be 90%. Extremely likely, 95% certain. Virtually certain is 99%. Now, these temperature changes that we've observed over the last century are actually, which is shown in this map, are uniformly warmer everywhere. And if you stare at the continents for a while, where we have enough observations, what you see is that the continents tend to warm more, and that the ocean areas tend to warm, have a lower rate of warming. And the only cooling response was here in the North Atlantic, in the oceans, over the ocean surface. Now, because I care about the human influence part, I'm going to go pretty rapidly through the observed state, the changes in the observed state of the climate system. And we can start with the atmospheric CO2. Since the modern measurements, the high precision measurements were made in the 60s at Mauna in Hawaii, we've actually crossed in some seasons in the high latitudes the 400 parts per million. Since pre-industrial times, we've actually had a 40% increase in the amount of carbon dioxide in the atmosphere. As a consequence, as a direct consequence of the rising CO2, the surface PCO2 in the oceans through gas exchange has actually risen, and the ocean acidity has also, the ocean pH has decreased, and therefore the ocean acidity has gone up. So CO2, the primary gas, is driving these changes in the surface ocean. If you look at Northern Hemisphere spring cover, since the 1920s, there's been a progressive decline. And since the period for which we have satellite observations on the trend here over that 30-year period is about 3 to 4% per decade. Between 1 and 2% per decade. I'm confusing my numbers. Between 1 and 2% per decade. For the Arctic sea ice, and particularly since the records from satellite and from direct observations, we've had a 3 to 4% decadal decrease. And the summertime, that's the annual average, has decreased 3 to 4%, but the summertime's actually decreased at 11% per decade. Now, one of the things that's really important from a kind of a physical perspective is what the oceans are doing. So the oceans are a key element of the climate system because they're where the ocean, where the heat can be stored. And so ocean temperatures have been warming up very strongly since the 1970s, where we have reliable data. Before the 1970s, we don't think the data is reliable, but after the 1970s, there's reliable data. And we see the ocean continually warming up through to the present. More than 90, and I'll talk a little bit more about it, more than 90% of the energy that's stored in the Earth system, is actually stored in the oceans. And the other effect of warming and the melt of the cryosphere and the melt of glaciers, the melt of Greenland and the melt of Antarctica is that global sea level has been rising. Modern day, the high rates that we see in the century since the 1900s actually comes from the comes from those three contributions: the warming of the oceans, the ice sheets and glaciers. The average rate since 1900 is 1.7 millimetres per year. So up to 2010, we've had 190 millimetres of total sea level rise. In the last part of this record here, where we have a little bit more in the way of measurements from both our altimeter and the tide gauges, we have a rate running at about between 2 and 3, and since 1993, about 3.2 millimetres per year. And if you think about all of this, right, these are covering the key elements of the climate system. The atmosphere, along with methane and nitrous oxides, the surface ocean, snow, the ice sheets, the Arctic ice, what the oceans are doing, global sea level, we conclude that the state of the climate system has changed and that warming is unequivocal. So that's the logic that gets us to this headline that is in the summary for policymakers. Now, it's all very well to say, yep, the climate system's changed, but what are actually the drivers of that and who's influencing it? So we tried to get to the question around human influences in the climate system. So this is a complicated figure, but the key and most important point is that this is the contribution from greenhouse gases in watts per metre squared, okay? And the most important greenhouse gas is carbon dioxide, followed quickly by the contributions from methane, halocarbons and nitrous oxide. This collectively is called greenhouse gases, and it is the biggest contributor to all of the other sources as obtained from measurements and the understanding of radiative theory through the atmosphere. And so the conclusion really is that radiative forcing from the changed composition of the atmosphere that we understand is the biggest, is positive, right? It's important that it's positive. We're driving the system and towards warming. Now, the atmosphere is a complex place and there are many contributors. And I just want to illustrate these time variations so that you get to think about what the main drivers are. So in the warming of the climate system, we think about what are the main drivers. There's the greenhouse gases, that's one driver. There's actually the contributions from aerosols. So man, through burning of carbon dioxide, actually emits a lot of sulfates and sulfate particles into the lower atmosphere, and those sulfate particles actually cool the planet. And you can see here that there's a negative signal. So we're running two experiments at once. Greenhouse gases to warm up the world. We're also pumping sulfate particles into the atmosphere, which cool the world down. And the cooling period in the 1940s, early 50s, is an example where the aerosol load actually exceeded the contributions from the greenhouse gases, and we did see a cooling in that period. So, and then there are some natural forcings. So one of the natural forcings is actually there are solar variations. And here you can see that on this yellow curve, the oscillations from the solar variability. And actually in the last 15 years, we've been in a downward phase from solar variability. And the other one that occurs is actually completely natural, of course, is the loading that comes into the atmosphere from volcanic eruptions, right? So we have explosive volcanic eruptions in the equatorial band which affect the upper atmosphere and cool the planet. We had beautiful sunsets during Pinatubo, for instance, and that is a very significant driver for a relatively short period of time in the atmosphere. So all of these things together are affecting the climate. But we can, from ocean measurements, understand actually how the planet is warming up. And this is a graph of this warming up, which is all the contributions from all the elements that we understand and have observations of. This is not a model, this is actually an assessment that comes from the observed systems. So the dotted lines here are the uncertainty. You can see that we're getting more measurements, and so the uncertainty is tending to close down in later times. But you can see actually that the ocean, the upper ocean and the deep ocean are the biggest contributors, and they're tending to just go up and up and up, progressively up to the present. And then the other components, land, ice, atmosphere, they, which are shown here, account for less than 6%, right? So 93% of it is really just stored in the oceans. So this is really important. This is a really important graph because if we know we've changed the atmosphere, you've changed the radiative balance, where's the heat going? You've got to have an answer to that. And the answer is it's going into the ocean and it sums up, right? So that's an important physical understanding of the climate system. So that's just the observational space. So if we want to understand how the humans are influencing this, we've actually got to think about how we model the human drivers in the climate system, so those radiative forcings that I just talked about. So here we take the land and ocean surface temperature, and we do the experiment using a numerical model where you can actually have just the single forcing. So we can have the volcanic eruptions and we can have solar variations, right? And that's all that's been driving the sophisticated climate models from the period 1910 through to 2005. And there are about 43 different, there may be 43 different models that have been contributed by all of the nations that are involved in this. And the envelope of those models, forced by our understanding of the physics of solar variability and the natural forcings, so the eruptions from explosive volcanic, has this envelope. And you'd look at this and you'd say, just looking at this, you'd say, those observations are inconsistent with the models using only natural forcings, right? So there's a very clear message that we cannot explain the observed land surface temperature field from just the simplest hypothesis around solar variability contributing and from volcanic eruptions. Volcanic eruptions are tending to cool the planet. So what you can do then is you can add in the response from the greenhouse gases, okay? So you can add in both the contribution of aerosols plus greenhouse gases plus actually the natural forcings, including volcanic eruptions. And what you find is, in this very simplified figure, but it comes entirely from the simulations of the climate models, is that the pink curve, so that's the uncertainty represented by all the contributions from all the nations, basically lines up with the observed temperature field for the global oceans. You would conclude reasonably that actually what we're seeing is that the observations can be explained by all of the forcings together. And in fact, because you know that the natural forcings is relatively small, all the contributions are really coming from the greenhouse gases and aerosols, both of which we have control over because their origins are from man. We can go a little bit further, right? It's not just the global things that we care about. We care also about at the individual continent levels. So you can do the same thing. So the pink band is the natural force, is the human influences plus natural forcings. The blue is just natural alone. And you can see actually by the later half of the 20th century, there's nice separation out between the anthropogenic forcings from those of purely natural variations for all of the continental regions, except, unfortunately, for Antarctica, and we can discuss that perhaps in the question time. So what we have here is really the attribution of warming of human influence at the continental regional scale, not just global, but continental regional scale for temperature. But an innovation on the fourth assessment report was that it was really important to actually think through what the human contribution was to all of this signal. And so we did an analysis across all of the what we call attribution studies and produced this figure. So there's quite a lot of, so here are the observations since 1950, 1951, so 0.6 degrees of temperature change. Here is the contribution that is attributed to humans from greenhouse gases alone, from what we call other anthropogenic, which is just aerosols. Here to natural variability, so this is solar plus volcanic eruptions, and this is the bit that's due to internal variability, the completely natural internal variations that occur in the climate system as best as we can estimate them. And if you stare at that, what you realise is because we're running two experiments at once, greenhouse gases tend to be compensated in part by the other anthropogenic. So you can combine those two together, and that's what this brown curve is, right? So these are both things that humans have control over. And what you can see is that the observations are almost perfectly well described by the anthropogenic contributions since 1951. The contribution from natural variability, the competing hypothesis for human change, is the eruptions and solar variation. It contributes nothing. And over that time scale, internal variability also contributes nothing. So we came to the conclusion that it was extremely likely that more than half of the observed changes could be described by humans. But actually, we wanted to go a little bit further than that, because if you look at that curve, you'd come to the conclusion that actually humans induced everything, the entire signal basically, but perhaps with a slightly lower confidence. And so he wrote in the best estimate of the human-induced contribution to warming is similar to the observed warming over this period. So what we've done really is we've brought together all our understanding of the physical science, and what we find is that through the mechanisms of attribution, which I won't talk about in this, is that we actually can describe all of the observed change. So if I had a message, the message is humans did it all. Okay, humans did it all for the global scale climate change signal on that time period. Now, there's been quite a bit of discussion in the literature, in the newspapers, around the question of the pause in temperature rise in the last decade. So the period 1998 through to 2010 has had a temperature rise of 0.05 degrees C, which is about half of the temperature rise we've seen since 1960, which is 0.12 degrees. And you can see this, so this is the same sort of graph, and you can see this pause that you see, it's just here. So this is from the period roughly from 1998, the last huge El Nino, through to the present. And it's interesting to look at the global versus global land. Global land is just the temperature change over the land surfaces, so ignoring the oceans. And you can see here that actually temperature hasn't really paused much. It's still going up on average. And if we look over the oceans, the warming is weaker, as I showed you in the kind of the observations of the world map. But you can see actually in this, when the mouse comes back, in this period here, that the oceans have actually been, the surface temperature of the oceans has actually been flat. So there's a clue here really that part of the reason for this pause is almost entirely due to the contributions from the fact that the oceans haven't been warming up as fast as you might have projected, as is shown by the red lines from the numerical models. So we've got to ask ourselves, what is really the explanation of that? So in spite of the first decade of the 20th century being the warmest, it's actually got a slightly lower rate. And here is the sort of IPCC explanation of this problem. Because we only have one Earth, okay, we can calculate the rate of warming for that single Earth, and it's shown here in the red. So this is 1998 to 2012, so that's actually the period which has a low rate. it turns out that from these, you can calculate that same rate for the 15 years before, 1984 through 1998, and you can see it's a high rate. Okay, and then we can take all of the climate simulations that we have, and you can calculate what, for this period of time, given that forcing from the radiation, what the distribution is for 15-year trends. And it is like this, right? Because in the world where we simulate these things, we can have many Earths. And there's no reason for these simulations to be phase locked in any way to the observations. They're done completely independent of the observations. And what you can see is this is the distribution. It's the same figure more or less for this period, slightly different rates, slightly different because slightly different forcings. Now, this is the short-term records, but if we take the longer-term record, the 1951 through to 2012, what you can see is that the observed warming, 0.6 degrees, corresponds very well to the long-term rate. So this narrowing of the probability distribution for the 60-year trends leads to a high degree of agreement between the observed trend for rising greenhouse gases and aerosols, et cetera, with the observations. So the question really is this broadening is to do with what we call internal variability. And we concluded that these are completely natural internal variations between an interaction between the ocean and the atmosphere can cause a substantial degree of the difference between the observations and simulations. So that's a partial explanation. But it turns out that if you look at the time history of the natural variability, that in the last 15 years in particular, we've actually had a period where there's been a few small volcanic eruptions which have been able to contribute aerosols to the upper atmosphere. And in terms of, this is watts per metre squared down the bottom here, those volcanic eruptions plus some other variability to do with aerosol loading, but the volcanic eruptions are actually leading to a negative. They're negative, so that means it's cooling of the surface. They're cooling the planet. So in the IPCC, after much work, we came to, how many people are colourblind here? Okay, that's excellent because I got a few red comments here. So the reduced warming trend of the last 15 years is due roughly equal measure to the reduced trend in the radiative forcing, so that's because there have been a few extra eruptions, and also because of the internal variability. And really, that is our understanding of the explanation for the last 15 years. It has actually nothing to do with climate change. It's entirely to do with the internal variability of the climate system, which is completely natural. And 15 years is way too short to actually ever calculate a trend in the climate in a changing climate. So I've talked all about temperature, and temperature's half the story. Another part is, of course, around water. What is the future of water? Can we detect a human influence in water in the climate system? And one of the nice things that we have over the last assessment is that we actually have more information of a type that actually allows us to talk more clearly about the human influences in the water cycle. So we've got lines of evidence around. There's the increase in atmospheric moisture, which is what's shown in this figure here, of which mostly the data is good in the Northern Hemisphere, and we have medium confidence about that increasing. So not a likelihood statement, a confidence statement, which actually means that we have less strong evidence in the case of atmospheric moisture, but there's clearly an increase in the atmospheric moisture overall. Global precipitation, the patterns have changed over land. It's very hard to actually measure precipitation directly, but over land you can see that the belts that are drying in the Mediterranean zone, similarly in the northern hemisphere, and also in the southern hemisphere, including Australia. And then you can see in the high latitudes to some extent, and in these regions, a tendency to, in the tropics, a tendency to increased rainfall, and in the higher latitudes. So global scale precipitation over land has changed and is sort of consistent with actually the projections of the changes in rainfall over the land surface. And I won't show a figure here, but we have actually very good evidence around a change in the extremes around heavy precipitation. So the 90th percentile has actually become more intense where we have observations. It turns out that the oceans have also been changing, and one of the revolutions, if I can put it that way, is that we've been making lots of surface measurements from autonomous instruments that are deployed globally over the last 20 years. And those, plus the other observations that exist in early times. And what we're finding is that the areas that are actually salty are becoming more salty, and the areas that are fresh are becoming fresher. So what we're saying really is that the areas that are already dry, so the surface is salty, are getting drier, and the areas that are actually got a lot of precipitation are getting fresher. And we have an index, and this index is the difference between the salty regions and the dry regions over the globe as a function of time. It's entirely based on observations. And what you can see is that since the 1970s, we've progressively been getting more salty in the salty areas and fresher in the fresher areas. And this is exactly the acceleration of the water cycle that we project in the climate models. We concluded actually that it's very likely and that the anthropogenic forcings have contributed to the ocean salinity changes in the surface. And if you use all of the lines of evidence that we brought together, both over land, the moisture change in the atmosphere, we thought it was likely that the anthropogenic influences have affected the global water cycle. So water is a really difficult variable to deal with, but actually this is evidence over the last 30 years of a strengthening of the water cycle, completely consistent with the consequences of rising greenhouse gases and aerosols in the atmosphere. We have other evidence as well. There's much more evidence, and we have much more confidence from just really what is 7 years more of data, but over a broader range of variables around the ocean warming, the changes in the global water cycle, the melting of snow and ice, sea level rise, and temperature extremes. We're not talking about the observations here, we're talking about the contributions man has made to all of these variables. So that's a big change from the last assessment report. And there was a iconic figure actually in the fourth assessment report, of which this is kind of a replica. But what this is really trying to show to you is that it's not a single variable, it's everywhere. The contributions of man in the Arctic are actually emerging out of the signal in Asia over all the land surfaces. Here, this is ocean heat content, so this is ocean temperature, so the North Atlantic, South Atlantic, Indian, Southern Ocean, South Pacific and North Pacific. We have an emerging signal of human influence driving the changes in the oceans. Arctic sea ice and Antarctica itself, we don't have an emerging signal in the same way, and in fact we can have a whole discussion about that. It's actually Antarctica is resistant to scientific understanding at the moment in terms of rising greenhouse gases. So it's all of these lines of evidence across the entire climate system which led us to have the headline in the summary for policymakers that human influence on the climate system is clear, right? We're trying, clear by the way is a synonym for unequivocal. So let's talk now a little bit about the future changes. Here we are looking at the projections. So we've established that greenhouse gases and aerosols are the chief forcing of the climate system at the global scale. And you can see that in these observations, this part of the record here, which is actually the historical runs. There's no observations on this, it's just the historical runs. And then what's new is these things in this assessment, which is called RCP. RCP is representative concentration pathway, but one way to think about it is a thing that is RCP 2.6 is actually a low emissions trajectory which actually would avoid 2 degrees of temperature change with reasonable probability. And you have a rapidly declining set of emissions going to zero basically by 2070, okay? And we have the RCP 8.5, which is an emissions which leads to high concentrations in the atmosphere and continuing to rise by 2100, but flattening out actually in the last decades of 2100. And here you can see that we've come since 1950, we've come just 0.6 degrees to 2100. If we follow, and that's a decision actually that mankind makes, if we follow the high pathway, 5% of the models will actually 5% of the models will be warmer than 5 degrees. 5% of the models will be cooler than, a bit cooler than 3 degrees, and that the average warming by 2100 is a bit over 4 degrees. So that's for the high emissions pathway. For the low emissions pathway, we almost stabilise at 1 degree here on average, so that's 1 degree since the 1986 to 2005, so you have to add another 0.8 degrees roughly to that, so that's just below 2 degrees by 2100. But 5% of models will actually be higher than the 1.5, and 5% will actually be a bit lower than 0.2 or 0.3 of a degree. So that actually, a mitigation scenario that follows that trajectory would be good news. So in the summary for policymakers, we do actually talk about how global temperature change is about likely to exceed 1.5 degrees relative to 1850 for all the scenarios. It's a slightly wishy-washy statement, to be honest. If you follow the high trajectory, it's a much more than that. And most of the detectable human influence is since the 1950. So if 5% of models were greater than 5 degrees, that's actually almost 10 times more than what we've seen in the last 50 years. Sea level will continue to rise. The upper bound for the high emission scenario was assessed at just under a metre. The average change is between 70 and 75 centimetres by the end of the century, and the lower bottom 5% of models for the high scenario will be a little bit above 0.5 of a metre. So if this was realised, that's 160 million people who would be affected within 1 metre of sea level. If this is realised, it's a much smaller fraction. You'll notice how in the previous figure, in the previous graph, the temperature scenarios separate out between the low mitigation, strong mitigation versus high emissions pathways. Sea level's a different variable because it involves the oceans and involves much slower processes of the heat take-up. And as a consequence, the emission scenario, the mitigation scenario, isn't enormously different from the high emission scenario. So what this is really telling us is we've actually locked a lot of change into the global ocean already. even if we were to actually mitigate strongly on the emissions trajectory. And this is just the difference between surface temperatures, which respond fast in response to change to emissions, whereas the sea level is a slow variable for which we've already committed to large changes. So this is the last figure, and it's actually a beautiful figure because it's the figure that kind of tells us about how our future carbon budget ought to be to actually avoid certain temperature changes. So it turns out that if you run these models to equilibrium, if you run this, sorry, I didn't say to equilibrium. If you run these models and you plot the long-term temperature response, what you find is, irrespective of these concentration pathways, they always fall almost proportional. So the cumulative, so the total amount that's emitted into the atmosphere of carbon dioxide shown here, and the long-term temperature anomaly relative to, say, roughly pre-industrial times, always falls onto a curve, basically, for all of the scenarios. So it's almost independent of the emissions trajectory we take. So it's sort of target independent in a way. But what you can see is that it has, so the final temperature anomaly looks nicely correlated with the cumulative amount of emissions into the atmosphere. So this pink curve is for these RCPs, and so this orange band also has some aspects of methane in it, some aspects of aerosols in it. If it was just pure carbon dioxide we emitted into the atmosphere, it would follow this black line, okay? And the nice thing is you can see the observations here for the historical record roughly fall on this same line. So you're now at United Nations, you're thinking about the framework for the Convention on Climate Change, and you know actually that you're supposed to avoid 2 degrees of temperature range. So they decided that was actually the temperature for which there was dangerous climate change. So if you're a policymaker, you can do the thought experiment. Okay, we want to avoid 2 degrees of temperature change. And if we use the atmosphere that we expect and project into the future, so we'd use the orange band here, and if this is the mean, and we want to be confident, let's say, by 66%, this is the 90% band, so 66% might be somewhere like here, then the amount of allowable emissions into the atmosphere would be something like 800 gigatons of carbon, okay? Now 800 gigatons of carbon, at the present we've actually come about 500, so we've actually used up more than half of our allowance of carbon to avoid a 2 degree temperature range. So what that means is that you've only got in your budget roughly 300 gigatons of carbon that you can emit further into the atmosphere before there's a 66% chance of crossing that 2 degree threshold. You can do a similar kind of calculation for 3 degrees or 2.5 or 1.5. And the good news, if there's good news here, is that actually we haven't yet exceeded the allowable budget for 2 degrees. We're still some distance away, so there's room to act, time to move. If we had defined dangerous temperature change as 1 degree, which is about here, we would have actually basically exceeded our allowable budget. So if you think about it, this curve is very helpful for thinking about what is the amount of emission we can put into the atmosphere to avoid any particular temperature. So if we want to limit climate change, we require substantial, very sustained reductions of greenhouse gas emissions. It has to drop to 0 actually by 2070, and it has to peak before 2020, roughly speaking. So just to sum up, these are the headline statements that began this 20-year process that IPCC has been undertaking. So back in 1995, in the second assessment report, actually the first assessment report was important, but it never said anything about humans' influence in the climate system. It didn't say there was a detectable human influence. By the second assessment report, they did actually get to say, oh, the balance of evidence suggests a discernible human influence. So it's a pretty weak statement, actually. We can just detect something. We can just see it. In the third assessment report, it's another 6 years' worth of data. The subject had moved on a little bit, so there's new and stronger evidence. And there's this statement here, most of the warming. So 50% is attributable to human activities, but there's no statement of how strong that likelihood is. So that didn't come until 2007, when everything is discussed in this calibrated likelihood language. And the evidence at that time, in 2007, was that most of the observed increase, so that's more than 50% of the signal in the global variables, was very likely, 90% certain, okay? So we were 10% chance of being wrong. And there was some commentary here that said that not only could we see it in the global scale variables, we could start to see it in the continental scale, so at continental averages. And in this report, what we've actually said is really quite a lot of much stronger statements. We've got more data, and there've been some refinements in the way we analyse the data and how we're able to bring multivariables and multiple lines of evidence together. And so we have the human influence is extremely likely, so more than half. Well, actually, more than half has been translated into the dominant cause, okay. But that's 95% sure. There's only a 5% chance. 1 in 20 planets would have perhaps a trend that's of that size. We've got the strong statement, human influence is clear. And we have, across things that I haven't talked about, for instance, heat waves. The human influence on heat waves has more than doubled the probability of the occurrence of heat waves. We have statements around the probability, very likely, for the salinity changes, which are responsible for the water cycle. So there's a growing set of evidence here in this report that just was not available in the last report. Thank you very much.